Hello again everyone, and welcome to our next lesson in this topic on the development of the atom. Our challenge today is to be able to describe the events that led to changes in the atomic model. Our aspire is to explain how the model has changed over time. The first theory we'll look at today is the theory of Democritus, who was around in ancient Greece, about 450 BC. Now, Democritus believed that nothing exists except from atoms and empty space. Everything else is opinion. And the essential gist of his theory was that there is an idea of an atom and that substances could be divided many times until you got to the smallest piece, which was an atom, or as he called it at the time, atomos, which means indivisible. His theory actually was not widely acknowledged at the time, as there was a much more popular opinion by a slightly more popular scientist who believed that everything was made out of earth, wind, fire and water. Now, we're talking thousands of years it took for scientists to start to actually acknowledge Democritus' work, and it mainly occurred when our next scientist came along. The next scientist was John Dalton in around 1803, and he did a lot of experiments. So when he came up with his theory, he had a little bit of evidence. He said that he agreed with Democritus, and he thinks that atoms are sphere-like objects. And he actually said that all atoms of the same element will be identical. Atoms cannot be created nor destroyed, only rearranged. And he also said that atoms could combine to form compounds. The next scientist was J.J.Thomson in about 1897, and he started to do some experiments as well. And he actually found the electrons in the atom, and he thought originally that the electrons would be embedded within the atom, just like in a plum pudding, or like it might be easy for you guys to visualise a chocolate chip cookie, and the electrons would be like the chips. Now, he discovered those electrons and he discovered that they had a negative charge. So in this atom, we've got to then imagine that everything else would have to be positive to ensure that it had no overall charge. He detected the electrons by using magnetic field to deflect the negative charge particles onto a detector. And there's a diagram of how that plum pudding could be arranged. Now, I'm going to show you a picture of a plum pudding just so you know what it might look like. It's a little bit like a Christmas pudding, like with the cake and the currants in the middle. The currants would be the electrons in this case. Now, J.J.Thomson had some really, really clever students, and his students did further experiments to try and confirm his ideas. They didn't quite confirm them, so let's have a look at our next scientist. So our next scientist is Ernest Rutherford. Now, he carried out an experiment to try and confirm the plum pudding model, but he actually ended up disproving it. What he did is he projected a beam of alpha particles at a very thin sheet of gold to probe the inner structure of the atom. Now, we're going to look at this experiment in a little bit more detail later on in this video. But based on the results that he gained, he actually announced that he found that the atom was mostly empty space. And what he found in the centre is, as he assumed at the centre, was a dense, positively charged piece of mass where the majority of the mass of the atom was concentrated. And he termed that the nucleus. Now, our next scientist, Niels Bohr, in 1913, actually looked at the electrons in a little bit more detail, and it's Niels Bohr that discovered the shell configuration of electrons. He found that there was more than one electron shell, first of all, and that the electron shells had different energy levels. So that's how we developed our knowledge of how electrons are arranged. But still no neutrons. So up to this point, we've got positive nucleus, we've got our electrons, we know where the electrons are located now, but we still have no neutron. And it actually took a while for the neutron to get discovered, and it was discovered by James Chadwick in 1932. Here he is. And it helped him to explain what an isotope is. So it was with working with isotopes that James Chadwick then made that discovery of neutrons. He did several different experiments to gather his evidence. But what we have to understand is the reason it was so difficult is because obviously neutrons have no charge. So they couldn't deflect them because they were chargeless, so they weren't going to attract to either of the other charges. Now, what I'd like you to do is I'd just like you to construct a timeline for the development of the atom. Even if you can just get the scientists in order, that would be amazing, and add what you can about each one. And we're just going to then go through it and make sure that you've added all the key points. So here's my timeline. I've added a couple of pictures and then I've got some text on the next one. So we've got Democritus, a Thomas, indivisible, and then we've got Dalton, tiny spheres, different atoms of different masses. Then we've got Thomson with the plum pudding model with the positive charge and the electrons embedded throughout. Rutherford with his positive nucleus and the electrons surrounding it with empty space. We've got Bohr with our electron configurations and that positive nucleus. And then we've got Chadwick with our neutrons and protons in the nucleus and the electrons arranged as Bohr had said. Now on the next slide, I'm going to give you some text that you can add to your timeline as well. Okay, so here are some text items, summaries that you can add to your timeline. I'll leave that up just for a little bit. Pause if you need a little bit more time and then press play when you're ready to resume. Okay, so just a little bit of a task for you to have a think about. I want you to try and explain why neutrons were the last subatomic particle to be discovered. Okay, so we've got to remember that neutrons have no charge and are located in the nucleus. So the fact that they have no charge would make it difficult to identify them, especially when scientists were working with quite limited technology. That's an interesting point to just make sure that we pick up on. You know, as technology gets better, our knowledge does improve. So whilst we might think some of these ideas were quite novel, they didn't have what we have now to back up their ideas. So we are going to now look a little bit further into the work of Rutherford. So I'm going to play a video. It's a Brian Cox video. It's really good. I've put the link on the screen if you want to go have a look at the original one, and then I'm going to ask you some follow-up questions based on this.
The mystery of how the electrons fitted inside the atom was eventually solved here in Manchester, in this building in 1911, by Ernest Rutherford. Rutherford was, in my opinion, one of the first proper particle physicists because he used beams of particles as projectiles to explore the structure of matter. Now, of course, in Rutherford's day, there was no such thing as a particle accelerator. So he used the decay of radioactive elements to produce his beams of particles. This is Rutherford's original desk. And in fact, if you hunt around a little bit, you can detect traces of radioactivity 100 years later. Rutherford asked two of his students, Hans Geiger and Ernest Marsden, to fire some alpha particles at a piece of thin gold foil and see what happened. So imagine these tennis balls are the alpha particles. Now, if the atom were, as Thomson had suggested, a kind of amorphous blob, then you'd expect the alpha particles to pass right through. And that's indeed what happened to most of them. But to their surprise, they found that around 1 in 8,000 bounce right back. After 2 years of puzzling over the meaning of these results, Rutherford realised that in order for the alpha particles to bounce back, they must hit something small and dense. So his new model of the atom was a bit like the solar system, with all the mass concentrated at the centre and the electrons orbiting like planets around the sun.
Today, we know that this picture isn't quite correct. Quantum mechanics tells us that we can't know precisely where the electrons are, but we can predict that they reside in distinct shells around the nucleus.
Rutherford's alpha particle scattering experiment was remarkably direct and simple, and it showed the nature of what the atomic structure is. By the way the alpha particles bounced off the atom, he worked out where the positive charge of the atom lives.
Rutherford had come to the astonishing conclusion that most of the atom, and therefore most of what we think of as ordinary matter, is in fact empty space. So if this apple were the atomic nucleus, the electrons would be a kilometre away.
After discovering the nucleus, Rutherford continued doing experiments, firing particles at different targets to delve into the structure of the nucleus itself. By 1932, Rutherford and his colleague James Chadwick had found that the nucleus is made of two kinds of particles, positively charged protons and electrically neutral neutrons.
The discovery in these experiments of neutrons, uncharged atoms of mass 1, has proved of great significance and importance, and has given us a much clearer understanding of the actual structure of nuclei.
Okay, so using what we've just seen in the video, what two conclusions did Rutherford find from his experiment? And then just a little bit of an extra stretch, how did Chadwick then develop that idea further? So the conclusions, first of all, most of an atom is empty space and there is a positive nucleus. They were his two main conclusions. Remember that Chadwick developed that further by identifying subatomic particles within the nucleus. If you want to be more specific there, it was the neutron that Chadwick specifically found. So it's time for us to move on to an exam question. So this is a bit of a long one, so I will read through it with you and highlight some key bits. Figure 1 shows the plum pudding model of the atom. This model was used by some scientists after the discovery of electrons in 1897. So you can see figure 1 there, you've got your ball of positive charge and the embedded electrons. In 1911, the scientist Geiger and Marsden investigated the effect of firing alpha particles at very thin sheets of gold foil. Their experiment is shown in figure 2. The arrows show the paths taken by alpha particles in the experiment. Explain why scientists replaced the plum pudding model of the atom with the nuclear model of the atom as a result of the experiment. Remember that the nuclear model is what we use today. In 1931, a scientist discovered that there are hydrogen atoms with a mass number of 2, as well as hydrogen atoms with a mass number of 1. A year later, another scientist discovered neutrons. Explain why the discovery of neutrons could explain the presence of hydrogen atoms with different mass numbers. I'm going to give you a little bit of time to have a go at this. If you need extra, just pause the video and then resume. Okay, so I've put the mark scheme on the screen for you to check through your work. A, most alpha particles went straight through, suggesting empty space. Few bounced back, suggesting a small central nucleus. And if they're positive particles bouncing back, then the nucleus has a positive charge. The plum pudding model does not explain these results, as it shows the whole atom as a ball of positive charge with no empty space. And then B, all hydrogen atoms have just one proton. Some also have one neutron. Protons and neutrons have the same relative mass, so the mass number of these atoms would be 2. Right, so just to add a little bit more jest on this, there is a song that goes through the history of the atom. A little bit annoying that it does miss out Chadwick, so you do have to add that one in, but I find it's really useful at learning the order of the scientists. So I'm going to insert it here. Please don't fast forward, listen to it. It's one of my favourites. There's a little musical interlude and you are allowed to fast forward it there. And if you want to go back and have a look at it, the YouTube link is on the screen and it's also in our Science Songs playlist.
Dalton, Thomson, Rutherford and Bohr, Schrodinger and Heisenberg and many, many more used their brains to venture in the realm of inner space and found the world of the atom was a weird and wondrous place. Dalton did experiments and said, I think it's clear atoms are tiny indestructible spheres. Thomson worked with cathode rays, said I disagree. A plum pudding model makes much more sense to me. A new chapter in atomic theory started to unfold when Rutherford played around with atoms made of gold. When a few of his alpha particles came bouncing back, he hypothesized the nucleus had knocked them off the track. Dalton, Thomson, Rutherford and Bohr, Schrodinger and Heisenberg and many, many more used their brains to venture in the realm of inner space and found the world of the atom was a weird and wondrous place. Bohr saw spectral lines for hydrogen and said, it seems to me electrons move in orbits with specific energies. Heisenberg said, forget it, there's no way to know the orbit or a path where the electron's gonna go. Schrodinger used lots and lots of fancy mathematics. It made a model of the atom based on quantum mechanics. It has orbitals, and those are based on probability. The atom is a fuzzy blob of pure uncertainty. Dalton, Thomson, Rutherford and Bohr, Schrodinger and Heisenberg and many, many more used their brains to venture in the realm of inner space and found the world of the atom was a weird and wondrous place. Dalton, Thomson, Rutherford and Bohr, Schrodinger, Heisenberg, many, many more used their brains to venture in the realm of inner space, found the world of the atom was a weird and wondrous place.
And I will see you in the next video. Take care, everyone.